Recording has started.
All right, hello everyone. Welcome to this eighth lecture. Um, Before starting, I think I have a quick comment about the project feedback. I've sent out comments on your project proposals in Canvas. Hopefully you will be able to see them. So most of the projects were okay, and I just had like minor comments trying to improve their quality or deliverables or kind of enhance the scope. But some of you have projects that are not very clear. So, for example, people were trying to do machine learning, and I couldn't figure out where they're going to get the data, what algorithms they're going to use. So they were kind of not very clear to me. So for those students, I would say please look at the comments and try to revise the proposal and make it more clear. And the rest of you, I think you can proceed with your projects. Um, so you can continue working on them for the rest of the semester, and hopefully the final project report is going to be due uh, in the final exams week. So this course doesn't have a final exam, but your projects will be due in that week before the semester ends. I think it's perhaps the second week of December, if I'm not wrong.
Sorry to have to say this, but I had an issue with my sound system. My headphones cut out. What was the first half of what you said there? Did you say that if we don't have any sort of warnings or notes on our project, to just go ahead?
So everyone should have a feedback by now. So if you go to your Canvas, you go to your project submission, you will have a comment on the abstract that you submitted. So please take a look. Some of you have already acknowledged and have responded to it, but some of you haven't. So maybe you've overlooked it. Okay, so if people have questions, just send me an email regarding the projects. So you're going to have like a week off before the final exam. So I think that is the best time that you finish up your reports and submit it. Okay, so let's get started with today's lecture. We've been talking about data compression lately, and today we are going to talk more about optimal codes that compress the data. So get started. When we say optimal, we really mean in terms of the average length of the code. Up till now, what we have learned is that prefix codes have to satisfy something known as the Craft inequality. So this is just a preamble from our last lecture. The Craft inequality says that you have to have code lengths that satisfy this relationship. Well, let's just mention for all I, 2 to the negative li is less than equals to 1. Okay, and I'm going to emphasize here that this is just for binary codes. And in general, it's going to be, if we have a D array code, it's generally going to be D to the power negative li, would be less than 1. and this is for a D array code, where D is some integer. So for example, ternary codes. So if we go to um, base 3, we have ternary codes. So they have symbols 0, 1, 2 instead of 0 and 1 binary. Or just say binary digits. So this is just a side note, giving you the general form of the Croft inequality. Now we've also mentioned last time that compression is measured in terms of the average length of the code. So compression is measured in terms of the average length, and we called it LCX. So the average length of the code C with ensemble X, and this was written as the expected length. So for all I, we did the sum of PI LI. Okay. Now the goal for today is try to find an optimal code, that is, try to minimize this length. So for an optimal code, the goal is to minimize the expected length. Okay, so that means we try to minimize this sum of PI LI, but we need to make sure that the Croft inequality is satisfied. So this means subject to the fact that there is a constraint as well. So for all I, 2 to the negative Li should be less than 1. Now this is an optimization problem, and I don't know how many of you have taken a course or have studied optimization theory. So I'm going to give you a brief overview of how problems like these are solved. So essentially, we have an objective function. So this thing here is the objective, which we try to minimize. And then there is this thing here, which is the constraint. Maybe I'll write it in a better way. Oops. Okay, so this thing here is the objective function. And here's the constraint. And another important thing is the variable of optimization. So we want to minimize the length So we're going to write this here, Li, I is greater than 1. Okay, so let's mention this part here as variable to optimize. So this is the classical form of an optimization problem where we have some variable to optimize over, and then we have an objective function that we want to minimize and some constraints. If we don't have constraints, then the problem becomes a little bit simpler because we can always take the derivative and then put it equal to 0. That's the normal way of optimizing or minimizing or maximizing something. But in this case, once you have constraints along with the objective, you have a problem that is a little bit more complicated, and we need a more sophisticated machinery to handle it. So just as a detour from today's lecture, we're going to study how these problems are solved. So let's just take a detour, and I'm just going to say from optimization theory. Generally, constrained optimization problems can be dealt with by constructing a Lagrangian. So Lagrangian, this is a technical term here. As follows. So for example, you want to minimize over x the function f of x subject to the constraint that some g of x is less than equals to h, then the Lagrangian is the Lagrangian function can be written as L is the function itself. So just let's call it L of x and lambda. Lambda here is the Lagrange multiplier. So we have this Lagrangian function that has f of x plus lambda times g of x minus h. Okay, so this is a form of the Lagrange function, and then we try to optimize this Lagrangian. So notice what we have done here is there is this original objective. So it has this objective, and then we have this penalty term. Well, this whole term is called the penalty term. So on top of the objective function, we are adding some penalty term, and we are always assuming this is lambda here is is a positive constant. So now if you notice, what is happening here is that the gx minus h is negative if the constraint is satisfied. So g of x should be less than h. So this term g of x minus h is negative. So what happens is we're trying to lower the objective function even further, which should not happen because then that would mean that we are having a value which lowers the objective function even more. So essentially, due to this fact, there is another constraint, not constraint, but kind of an auxiliary result that's called complementary slackness, which means that this second term should overall be zero at best. So I'm going to write here a few comments. So then we solve curly L by curly X, partial L over partial X equal to 0. So we try to minimize or try to take the derivative of the Lagrangian and put it to 0, along with the fact that lambda times g of x minus h equals to 0. So this term or this fact here is called complementary slackness. What it means is either the coefficient lambda is 0 or this constraint is satisfied with equality. So if we are at the edge of the constraint, that means gx is exactly equal to h, then obviously we have achieved the limit. So we are within the constraint and we are trying to minimize our function. But let's say yes.
I have a question here. So we just added this term, and now we're assuming it's 0 anyway?
No. So basically, the product is 0. So that means overall this term does not change the value of the overall function.
Right, but if that's true, why do we add it in the first place?
So the thing is, so it's like a penalty. So at the optimal point, this whole term should not contribute anything. But let's say we are not at the optimal x, then this term should penalize it. So you should get a value that is not optimal.
Right, but are we trying to minimize f of x, or are we then trying to minimize the penalty term then?
So we are trying to minimize this function, and the minimum value of this function is when the second term is 0 and the f of x is minimized. Do you see this?
Yes.
So if the second term is not 0, then you are basically minimizing f of x and some other function, which you do not want. You want to minimize.
Right. So f of x plus something is larger than f of x.
Yeah. But if at the optimal point the second term is 0, then you are essentially minimizing f of x and also making sure that your constraint is satisfied.
Right, but again, what happens if g of x is less than h? At that point, then we're subtracting something from it, and that lets us optimize a function smaller than f of x.
Right. So then your lambda will change, and then it will compensate it. So lambda is going to either be zero or be some other value that compensates it. So the thing is, we try to enforce this condition and then solve for both x and lambda. So instead of just optimizing for x, this is a condition that we impose. We want to make sure that if this constraint is not satisfied, then your lambda is zero. If your constraint is satisfied exactly, then it's great because any lambda will be okay. So your penalty has these two terms. One is lambda, one is this constraint. Basically the difference. So
Okay, so we should either set lambda to 0 or g of x minus h is 0, such that that term is 0 and we can minimize that.
So we don't set anything. We just put a condition that the product of lambda and g of x minus h is equals to 0. Then automatically it enforces this condition that either lambda is 0 or g of x minus h is 0.
Okay.
That's a very, very standard way in optimization theory that people use to handle constraint problems. And
that still causes one last issue, though, because, okay, we can make sure it's 0, but if it's 0, then it doesn't affect L of x and lambda.
What do you mean?
If we're saying that entire term is 0, then you're basically adding 0 to f of x and then solving, which is the same as f of x. I'm not really sure why we have that in the first place.
Okay, so the thing is, I should put here a star. So does that make it a little bit better? So
Not quite sure what that's supposed to mean.
Well, let's put a star everywhere. So that means the optimal x and the optimal lambda satisfy this equation.
Okay.
Okay, so not every x. So you have this penalty term, and this is not 0 for arbitrary x. But at the optimal x and lambda pair, this condition is satisfied. That means if you're able to find that x and lambda, you are essentially just minimizing the objective, not the anything else. So the second term is not contributing to your. I should have put a small example here to show you how it works. But I mean, you can construct any. So let's say you want. So for example, you want to minimize x squared. Okay, subject to x is less than equals to what? -1. So I know that the x squared is like this, and if I purposely, enforce that x is less than -1, then the optimal is this, isn't it? Instead of the 0.
Right, so that makes sense.
Just 1, right? So I mean, what I'm trying to do here is let's form a Lagrangian. So it's going to be x squared plus lambda times x plus 1. And now if I take a derivative, um, curly L over curly X, it's just an example that I construct out of my head. I don't know how it's going to work. 0, right? And then this means that lambda is negative 2x. So now lambda times x plus 1 equals to 0 will give me lambda equals to 0 or x is negative 1. Okay, so that means x is negative 1 is the optimum. So, I mean, from here, it will go to the fact that minus 2x, x plus 1 equals to 0, which says that x is 0 or x is negative 1. Okay, but this one is not possible, so we pick this. So therefore, x is negative 1 minimizes the function. Gives me this horticulture stuff is working at the wrong time. Can you still hear me?
There are weird noises in the background of the audio, but it can
Yeah,
technically make out what you're saying.
people have started working at the wrong time. I hope it will take a minute or so. So, constraint optimization problem. So, I mean, there's a whole literature on how people solve optimization problems, and this is not going to be the topic that we study here, but I just want to borrow this from the literature and try to show you how it works in this context that we are talking about. So, circle this. Okay, so now our problem was trying to minimize this expected length, so the sum of pi li, subject to the fact that 2 to the negative li is less than or equals to 1. So let's try to follow the same procedure. So for our problem, to solve the constrained or what should we call it? Solve the optimal code problem. The Lagrangian can be formulated follows. So our Lagrangian will be sum over I, pi, li plus lambda times I 2 to the negative li is minus 1. Right, so that's coming from the constraint. And we need to solve, actually I should write this as L of pi and lambda. So we need to solve curly L over curly pi equals to 0 and lambda times minus 1 simultaneously. For optimal, oh, this shouldn't be with pi, with li, sorry. And this also is a function of li. So we're trying to find the optimal lengths of the code. And what happens is if you do curly L over curly li, so we're looking here. Okay, so if we try to take the derivative of this with respect to the lengths, what we're going to get is, because it's a summation of pi, li, so if we take the derivative with respect to li, it's going to be just pi plus lambda is there. Then what you have inside is just derivative of two to the negative li. Okay. So does anybody know how to take the derivative of 2 to the negative li?
Quick question. We took the derivative of a summation and we ended up just with pi. How did that happen?
So we are taking the derivative with respect to just the ith term. So this is a good question. I mean, maybe other people are also thinking about the same thing. So I should just write it as a, maybe let's just expand it and write it. So you're trying to do curly over curly li of this sum plus lambda times this. Okay, so let's just expand the sum. So we're going to write dot 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 plus pi minus 1 li minus 1 plus pi li plus pi plus 1 li plus 1. Okay, so it's a partial derivative, so any derivative of anything except the ith term is going to be 0. And the same thing happens here. So we have a lambda here, and we have dots 2 to the negative li minus 1 plus 2 to the negative li plus 2 to the negative li plus 1 dot dot dot, and then minus 1. Is it clear now?
So it basically just zeroes out all the L terms that aren't L sub I since we're solving with respect to L sub I.
Exactly. Right. So
Although now I'm wondering what happens since There are all the other i's other than the one we're currently testing with.
We're solving it for the ith term. If you're able to solve it for ith term, then it's true for any I. I mean, then it gives you a general result. So let's try to see how it works. Okay, so does anyone know how to take the derivative of 2 to the negative li with respect to li? No? Okay, so let's write a side note. So 2 to the negative x, you want to differentiate it with respect to x. That's how you do it. So let y equals to 2 to the negative x. Okay. Then you take log on both sides, or take natural log on both sides. So you have ln of y is negative x ln of 2. Now you differentiate both sides with respect to x. And what that makes is 1 over y dy over dx equals minus ln of 2. So then dy over dx is minus y ln of 2. So the last step here is you substitute y equals to what you assumed in the beginning, which is 2 to the negative x. So therefore dy over dx is minus 2 to the negative x ln of 2. I mean, I don't expect you to know this, but uh, it's an exercise rarely done in calculus, but it's important to know. Okay, so let's just keep this as a note here and try to figure out what the derivative is going to be. So we have pi plus lambda times, so instead of x we have li, so our derivative is going to be minus 2 to the power minus li ln of 2, and this equals to 0. Okay, so from here what we have is 2 to the power minus li lambda ln 2 equals to pi. So 2 to the negative li equals to pi over lambda ln of 2. Okay, so that's one equation that we get from taking the derivative of the Lagrangian. Okay, so now the second thing, as I told you, the complementary slackness condition that comes from the constraint. So that was lambda times the sum of I 2 to the negative li minus 1 should be equal to 0. This was the second equation. Okay, so let's substitute 1 in 2. So you will have lambda times the sum of I pi over lambda ln of 2 minus 1 equals to 0. This gives you lambda times, so this thing here is equal to 1 because you are trying to sum of all the probabilities. So you just have 1 over lambda ln 2 minus 1 equals 0. And this is going to give you lambda is 1 over ln of 2. Okay, so you've got your lambda, and now the only thing left is finding Li. I think I should put lambda star here, so that's the optimal lambda, and substituting this back into 1, equation 1 is going to give you the optimal L. So 2 to the negative Li star is equals to pi over lambda star ln 2. Is going to be 2 to the negative Li star is pi over 1, right? Well, 1 over ln 2, and this cancels. So now what you have is simply minus Li star is log 2 of pi. So Li star is negative log 2 of pi. And essentially Li star is log 2 of 1 over pi. So this is the final result. Okay, so let's write this in a formal statement. So for an optimal code, the code length, the code word length, that is phi, Li equals to log 2 1 over pi. Okay, and for such a code, the expected length is going to be LCX PILI. This turns out to be PI log 2 1 over PI, and this is essentially equals to the entropy of the X. So therefore, if optimal lengths are used for code words, then the average length of the code achieves the entropy of the source. Okay, so that's the key result here, that if you use optimal lengths for code words, your average length of the code is going to be equals to the entropy, and that's the minimum number of bits required to represent the source. And that's kind of the maximum compression that you can achieve. So all the calculus that we have used to reach here, I don't expect you to know all of this, but at least to get here, we needed that formalism. And it's good introduction for some people who have never come across optimization and constrained optimization problems. It is really a standard way of doing things, and it's very useful here as well. So now what we have shown is the lengths of code words that should be there, but how do we construct codes that achieve these lengths is the next topic for today. So that's going to be the Huffman code. And Huffman is really an algorithm that tells you how to construct prefix codes of optimal length. So before starting our discussion on Huffman, let's just write a few comments here. So assuming there is a source, well, maybe just start with the Huffman. So it's an optimal length coding algorithm. Okay, so the key idea is assuming a source with symbol probabilities P1, and assuming they're in descending order, so P1 is bigger than P2 and so on, and is bigger than PM, then there exists an optimal prefix code that minimizes the sum of Pi Li subject to the constraint on Kraft inequality. So subject to the fact that 2 to the negative Li is less than equals to 1. Okay. And the properties of such a code are, so number one, if Pi is bigger than Pj, then the length I is shorter than Lj, so it's less than equals to, because obviously they can still be equal. The second property is that the two longest code words have the same length. And finally, the two longest code words only differ in the last bit. In their last symbol. So some of you might already guess that these codes, which are prefix codes, are kind of on a tree. So on that tree, we try to assign the codes to symbols, but what we have is that symbols that are more probable, they will try to get shorter codes, shorter length codes. So they're going to be early on in the tree, and symbols that are more probable, that occur frequently, they are going to be assigned on shorter. So more probable symbols will have shorter codes, and less probable will have more or longer codes. And these are on the tree, so any two longest code words are going to have 1 bit difference, and the longest code words are going to have the same length in terms of the bits. We'll see this with an example when we start this Huffman coding procedure. So what Huffman code does is really gives you a process, a simple algorithm. So Huffman code is, or provides, a simple algorithm to construct an optimal, again, when we say optimal, it's just the shortest expected length. It constructs an optimal prefix code for a given distribution, probability distribution of the source. Okay, so now we've set the preamble of Huffman coding, and now we're going to look at an example. So let's say that we have a source having symbols A, B, C, D, and E. So let a source have symbols X is A, B, C, D, and E with probabilities Ex is 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.25, 0.2, 0.15. Okay, so construct a Huffman code for the source. Okay. Now, I'm going to work out the algorithm first and then write the steps for it, because probably it's easier to understand that way. So let's construct a table. So we're going to have the source symbols X, and then I'll have like a few steps. So step 1, step 2, okay, so in every step we're going to work with the probabilities. So let's write down the symbols. So symbols are A, B, C, D, and E. And in the first step, we arrange the symbols in descending order of probabilities. So we write the symbol with the highest probability first. In this case, fortunately, everything has already been ordered. So the first symbol has the highest probability, second has the second highest, third has the third highest. So we have an ordering that is there. So it's 0.25, 0.25, 0.2, 0.15, 0.15. Okay, so really the first step asks you to arrange the symbol probabilities in descending order. Okay, which is already done here, so we just wrote them down. Now, next step, we want to combine the two smallest probabilities into one. So we combine them and add their probability to one. So here in this case, the smallest two are these. So we're going to combine it, and so their sum is going to be 0.3. So that's how we combine it and move it to the next step. So both of these have actually merged into the probability, which is 0.3. Okay, and now we are going to label them as well. So whenever we combine things, we label them with bits 0 and 1. So we write a 0 here and a 1 here. Okay, and the remaining probabilities move to the next stage as it is. So every step you try to combine just one. Okay, so let's write down what we did here. So step 2, we combine two smallest probabilities and label the leaves. Okay. Now again, we're going to do the same thing. We're going to combine the next smallest. So the smallest two this time are 0.2 and 0.25. So we are going to combine this and this one. So this turns out to be 0.445, and the remaining come as it is. So 0.3 is going to stay as it is. Then we have 0.25. And again, we're going to label these leaves with 0 and 1. Okay. Now, again, the same process. This time the smallest two are 0.25 and 0.3. So we have this here, and then we have this here. So this turns out to be 0.55, and this comes as it is as 0.45. Again, labeling 0 and 1 here. The same thing. This is the final stage, so when we combine these two, we just get 1.0. And again, labeling these as 0 and 1. Okay, now we have labels. So for every symbol, what we have to do is read out these labels backwards. So I'm going to try to so maybe here I'm just going to say so read 3 backwards to find the code.
Isn't there supposed to be something about the 1 or the 0 is always on the side that's larger instead of this? I don't think we're following that rule.
Which rule, 0 and 1? Okay.
So on step 3, the 1 is pointing toward 0.3, which is larger than 0.25. For step 4, the 1 is pointing towards 0.45, which is smaller than 0.55.
No. This 0 and 1 is a label. You can flip it. I mean, this doesn't matter.
I thought there was a thing somewhere about you're supposed to have the larger one on the certain side.
Well, I mean, there are many different conventions that people can use, but actually it doesn't matter in terms of the length. So eventually the code can be not unique, but the lengths are the same. Okay, so instead of using 0 and a 1, you can actually use 1 and a 0 here. The same thing everywhere else. You reverse the convention, your code is going to be complementary of this, right? So it's going to be, wherever it's ones, it's going to be zeros, but the length is going to be still the same. Or am I missing something? Is there a rule saying this?
In the guides I've been looking at for my project, it seems to have that, but I'm not sure of the reason.
Give me a moment here. Let me just look at the convention that's used in your book. So there are many different variants actually, and your book doesn't seem to have this. So it's not going to save you in terms of the number of bits, but maybe it has some other properties if you do that. I mean, you can still do it, but in this case, I'm going to follow this simple labeling. Okay, so, and where do you see this violated? Which step were you referring to?
Okay, so in step 4 and step 3, the direction that the 0 and 1 point to differ. For step 3, the 0 points to the smaller number. For step 4, it points to the larger number.
Okay, I got it. No, I think this is not a convention. It may be in some other variant. So there may be variants where people prefer to do something, but in terms of the length, is not going to matter. So let's see. what the code eventually is. So I'm going to read it backwards, but before that, let's try to see whether I can shrink it. No. Okay, so I can't. Anyway, just let's read it backwards. So for the first one, the symbol A, we read it this way. So it's going to be 0, 0. For the second symbol, it's going to be 1 and 0. Okay. The third symbol is going to be 1, 1. Oops. There's going to be just 1, 1. So there's a 1 here. So you follow this path and okay. For the third one, it's going to be 1, 1, 0, and then no. So it's going to be 0, 1, 0. And for the last one, it's going to be 0, 1, 1. So 0, 1, and 1. Yeah, I'm going to erase this, but let's use different colors to. For the first one, it's simple because it's going to be, right? This is the path. Let me circle them. So the code is going to be 0, 0 here. Let's use the same. For the second one, it's going to be 1, 0. For the third one, it's going to be 1, 1. So to reach here, we traverse this path. I'm sorry we have to mess this up, but for this example, it's going to be messed up. Next time, we're just going to write it directly. And for the next one, it's going to be 0, 1, 0. And last one is going to be going to be 0, 1, 1. Okay. So the Huffman code is A, B, C, D, E. We have 0, 0, 1, 0, 1, 1, 0, 1, 0, and 0, 1, 1. So the length is 2, 2, 2, 3, and 3. And if you work out along with the probabilities, so Px was 0.25, 0.25, 0.2, 0.15, and 0.15. And if you work this out, you will see that actually this is going to be achieving the entropy. So the expected length is going to be I'm not computing it here, but you can actually verify that this code will achieve the so let's just write it here. L the X is going to be 2.3 bits, and H of X is 2.2855. Okay, so you see that basically um, if you round it up, floor it, it's going to achieve the expected length, which is equal to the entropy. Okay, so this example was a little bit messy. I think we can do a more detailed example now. It's important to learn the process because it's going to be in your homework. Uh, maybe a quiz, I'm not sure. It's easy to give it in a quiz or not, but so this example says consider a source with symbols 0, 1 up till 7 with px equals 0.35, 0.25, 0.1, 0.1, 0.1, 0.05, 0.05. Okay, so let's work out the Huffman code for this. So we have these symbols, and then we have our steps. So let's just write 1, 2, 3, 4, 5, 6, 7 here. And this step 1 is going to be just the probabilities in descending order. And again, they are luckily in descending order. So remember, I mean, in your homeworks or some other quiz, you may have a mix up of probabilities, so they may not be in descending order. So your goal is to try to fix them and make them in descending order. So the first step, arrange. Okay, it's 0.35, 0.25, 0.1, 0.1, 0.1, 0.05, 0.05. And now it's again, step 2 is simple because they are in descending order, so the last two are the smallest one, so you combine them. Write 0 and 1 here, which becomes 0.1, and the rest just follow. So step 3 now is you combine the next smallest one, so it's going to be these two. I'm going to use a different color for the labeling here. This one is going to be 0.2 here, 0.1, 0.25. Okay, so the next step, the next smallest are 0.1 and 0.1, so we combine these two. Label these step 5, 6, 7, okay. And then probably code if possible. Okay. So now the next smallest are point 0.2 and point 0.2. So these come up to 4. 0 and 1. And the next step, smallest one are 35, 25. That's going to be, hopefully I'm not making a mistake. Keep watching. So it becomes 0.6 and 0.4. And then these add up to, 1. So there is this labels here. Okay, so if we try to read the code backwards now, what is the code? What's the code for the first symbol? Is anyone there?
Yes, we're listening.
Okay, so what's the code for the first symbol? So we
Zero,
want to make it
zero.
read backwards, yeah. 0, 0. How about the next one?
0, 1.
Right, so we read this line here, 0, 1. And then this way, so it's going to be,
1, 0, 0.
yeah,
101.
no, 101, yeah. Then 1, 1,
1,
0.
0.
Then it's triple 1, 0. Then triple 1, 1. Okay, so we can always write the length of these. Just length 2, length 2, 3. These are length 4. So again, as before, you can always find the expected length of the code and compare it with the entropy. That should be a simple exercise for you. In a nutshell, the procedure of sending a Huffman code is really to arrange probabilities in descending order, then combine the smallest 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 two probabilities and assign bits to the leaves, and then repeat this process until all probabilities have been combined. And then the final thing is to read the tree backwards to to assign codes. Or okay. All right. Okay. So this is the end of the Huffman coding process, and before leaving it, I think we should just some remarks on Huffman. So first thing is it's a simple and easy process to obtain prefix codes of optimal length. Oh, by the way, can we check the log2 of 1 over pi? So log2 of 10 is how much?
3.32.
So, okay, that means
Specifically, it is very slightly less than 3.322.
No, but there's a floor, a ceiling operation on it, so it has to be like 4 bits,
Right.
right?
Yeah, that's what happens
Yeah,
in reality.
probably I need to check these things later on and make it correct. Okay, so I mean, even though Huffman coding is a very simple and easy process, but there's limitations to it. So, however, the probabilities of source symbols need to be known in advance. Okay, so a lot of times this may not be possible, and you may want to estimate them over the fly. So that kind of limits its applicability. Then a lot of the times probabilities keep changing. Keep changing according to the nature of the data. We just cannot say that images have these sort of probabilities and text has these probability distributions. So in that case, you may have to embed the tree itself or the code itself with the data. So the code itself may need to be embedded to the data stream, or just the data. Okay, and a lot of times this may be inefficient. So it's not just the compressed data stream, your coding strategy or the coding um, kind of the auxiliary components, the code have to be embedded as well.
I actually did some research on this, It's something that came up since I was doing this as my project. There's something called the canonical Huffman code, which allows you to not embed the code dictionary, but some kind of fact about the lengths of the code that allows it to be reconstructed to not only the equality of the code digits to the actual values, but some other stuff too. That's supposed to be the optimal route for encoding the code itself alongside the optimal code, but I cannot figure out how it works.
So, I mean, the canonical code um, will not be efficient in all cases. There's going to be, in some cases, it might work well, and in other cases, it may just
Yeah,
be terribly
there are
bad.
still corners. It's better than
Yeah.
embedding the whole tree, though, but I can't figure out how to actually implement.
Well, it depends. If the data is very large, then embedding the tree may not be a big deal. So it
Exactly.
depends. So
It's one of
if
those
you're,
as it tends towards infinity things.
yeah, right. But given its simplicity and its properties, people may still want to use it. But in real life, this is rarely used. Probably next lecture, we're going to talk about some codings that are actually used in real world, like JPEG and WinRAR and stuff like that. So those are called stream codes. So you don't have to know all the source probabilities in advance. But anyway, today our topic was Huffman coding, and which is kind of the optimal code. But I also want to mention another suboptimal code. It's not exactly optimal. It's a little bit um, ways away from optimality. That's called the Shannon-Fano alias coding. So just the final topic for today is and just one example of this code, the Shannon-Fano alias coding. And it's a procedure that uses cumulative distribution to construct code words. And I mean, this process is a little bit more complicated than the Huffman, but it is one code which is good, but is suboptimal in terms of length. So code words lengths are, log 1 over px with a ceiling operation plus 1. So instead of being just the ceiling of log of 1 over p of x, there's one extra bit. So just a refresher here, the cumulative probability distribution is defined as capital F of x, and it's a sum of I mean, if you talk about the discrete case, it's just the sum of all the probabilities which are less than or equals to x. Okay, so we're trying to add up all the probabilities up until the symbol x. There's also, for this course, a kind of modified cumulative distribution function. F bar of x is defined as f bar of x is the sum of all the probabilities a less than x. So note this is very important here. So this is a less than equals to x. This is a less than x, and plus you just add half of the probability of x. If I add more clearly, this term is really the previous cumulative value. And if I draw a figure of how cumulative distributions look like, and this is x, this is a cumulative distribution x. Cumulative distributions really are staircase type of distributions or staircase type graphs. So you may have something like this. Things like this. And it goes all the way to 1. So, so let's say this is some x here, and this is your x minus 1. This is going to be f of x. This is f of x minus 1. And your f bar is going to be in the middle. Okay, so this whole of this is p of x, and your f bar is really f of x minus 1 plus p of x over 2. Okay, so this is a modified cumulative distribution function, and it's used in this Shannon-Fano-Alias coding. Hopefully this is going to be clear with an example. So if example of Shannon Okay, so let's take an example where x are the symbols 1, 2, 3, and 4, and their probabilities are 0.25, 0.5, 0.125, 0.125. So now cumulative distribution is easy to compute. So the first cumulative distribution value is just the probability itself. So it's going to be 0.25 here. The next one is going to be the sum of the, so we add them up, right? The better way to do it is just add these two values, we get 0.75. The same, I mean, whatever we get from here is going to be 0.875. And we add, we get 1. So what is f bar of x here? F bar is I'm not going to write how it calculated, but it's f of x minus 1 plus 0.5 p of x. So the first one is going to be just half of this, because f bar of the previous one, f of the previous one is 0. So it's going to be just the half of this probability. The next one is going to be 0.5. Then we have 0.8125, and then 0.9375. And let me know if you still don't know how to compute this f bar for this example. Okay. Hopefully.
So this should basically be treated as a recursive function, not a direct sum then.
It's not recursive. It's just depending on the previous value. But in some way, yes, the previous value depends on its previous value, so it's kind of recursive. But if you just look at this table here, you just need a previous number. And
right. Yeah, it's not truly recursive because we're not adding 0.25 to 0.125. We're adding it to 0.25 again. It's only the last term that's the 1/2. That's
right.
How do we determine what the p of x's are? Is that just whatever order they're written down in or occur to the encoder in?
Yeah, so p of x is the probability here.
And then also, the p of x's, we don't just randomly receive a packet that says what the p of x is. We receive a packet with a certain value and then have to compute the probability. How is this helpful then if you don't have the probabilities in the first place? Because that's what I assume the cumulative.
Yeah, so no, that's the universal question. How do you know the source probabilities? So either you estimate them, right? So you have a data set, and you can figure out using a histogram or some way to figure out what the probabilities are. And once you have those, then the idea is there are these schemes like Huffman encoder and this Shannon-Fano coding that can help you compress the data probabilistically. So again, it's not going to be, in some cases it can be bad, but overall, on average, it should reduce the length of your data. And for these codes, you need to know the probabilities. That's the trouble. Hopefully for this stream codes, lesser information about probabilities is required. And there's a way to estimate it on the fly as well. Right, so if you have a stream of data, you try to make an estimate of the probabilities and then use them to encode the data and so on. Right, so that's why this is probabilistic. You cannot always just universally give a symbol a certain code. So it depends on how probable it is and what's the profile. Okay, so if we have this cumulative distribution here, we can compute this modified cumulative function. And the next thing, which is even more tricky, is you want to find f bar of x in binary. Okay, and again, I'm not expecting you to know how to convert decimals into binary. It's something I think a lot of you might have not been doing in a long time. So let's just give you a refresher here. So how to convert decimal in binary. So for example, you want to convert 0.125, right? So what you do is you do 0.125 times 2. What you get? Let me do it on a
We
calculator.
have 0.25.
So you have 0.25, and you pick the integral, the integer component. Then the remaining 0.25 you try to multiply again with 2. What do you get now? 0.5. Okay, so we pick this again, then the same process. You take the leftover, which is 0.5 times 2, and you get 1.0, then you take this one. Okay, and the next time it's just 0 left. 0 times 2 is 0. So 0.125 in binary is 001. Okay, I mean 0 point. It's 0.001. Okay, which is basically, so let's just write it. So it's 0